Welcome to The Explainer. Today, we're talking about a technology that literally promises to put the power of a star in a bottle. We're going to dive deep into the future of nuclear energy, comparing two totally different approaches. Fission, which is all about splitting atoms, and fusion, which is about joining them. We'll look at what goes in, what comes out, and ask the big question. Could one of these be the ultimate clean energy source? Let's get into it.
You know, the race to decarbonize our planet is on, and it is a massive challenge. But experts like Maria Zuber over at MIT are pointing out something really important. We're probably going to hit a ceiling with renewables. To truly get off fossil fuels, especially for that reliable 24/7 power we all depend on, we're going to need another heavy hitter, another huge zero-carbon option.
So, what's that option going to be? Well, here's our roadmap for this explainer. We'll start with why we need a new energy source in the first place. Then we'll get into the wild idea of nuclear fusion and how a recent miracle in magnet tech totally changed the game. And finally, we'll put fusion head-to-head with its older cousin, fission, focusing on that one critical issue everyone talks about, radioactive waste.
Okay, let's dive right in. Our world is hungry for energy, and that demand is only going up. So why aren't the clean energy sources we already have quite enough to get the job done?
Here's the core of the problem, right? Solar and wind are fantastic, but they're what we call intermittent. The sun isn't always shining, and the wind isn't always blowing. And because of that, projections from places like MIT suggest that by 2040, we could max out how much they can do for our grid. We'll still have this gap, a need for a powerful, clean energy source that just runs day and night. And that gap is what scientists are in a mad dash to fill.
And that brings us to a potential solution that sounds like it's straight out of a sci-fi movie, but believe me, it is getting very real very fast. We're talking about nuclear fusion. So, what on earth does it mean to put a star in a bottle?
Well, it's pretty much what it sounds like. As Robert Mumgard from Commonwealth Fusion Systems says, it's about copying what the universe does best. Fusion is the engine of our sun. It's what powers every star you see in the sky. And the whole idea is to harness that incredible cosmic power source and build a miniature version of it right here on Earth.
So, how do you bottle a star? The most promising design we've got is this thing called a tomacac. And you can basically just picture it as a giant magnetic donut. What it does is use these incredibly powerful magnetic fields to trap hydrogen gas, and then it heats that gas to over 100 million degrees Celsius. I mean, it gets so hot it's not even a gas anymore. It turns into a fourth state of matter called plasma.
Right, but if fusion is so great, why don't we have fusion power plants everywhere? For decades, it was a running joke in the energy world that commercial fusion was always 50 years away. It turns out, that whole time, there was one single massive roadblock holding everything up.
The problem was the magnets. To get a fusion reaction going that actually produced more energy than you put into it, the magnets you needed had to be gigantic. Think the size of a city block. The cost, the complexity, it was just totally impractical. But then, very recently, a breakthrough in magnet technology completely changed the game.
And this is it. These new high-temperature superconducting magnets, or HTS magnets for short. Now, without getting too deep into the physics, what they do is allow you to create an immensely powerful magnetic field in a much smaller space. And you can see how that changes everything. A stronger field means a smaller device, and a smaller device means you can build them faster and cheaper. It's a total game changer.
And get this, to put it into perspective, the team at MIT and Commonwealth Fusion Systems used this new tech to double the strength of the magnetic field. This was a leap that people thought would take decades to achieve, and they did it in just 3 years. That's not just progress, that's a massive acceleration down the road to fusion energy.
As Maria Zuber says, this is the miracle everyone was waiting for. This wasn't some tiny, incremental improvement. No, this was the key that unlocked the whole puzzle. It makes building commercial fusion plants a real possibility and on a timescale that could actually help us in the fight against climate change.
Okay, so now we know the big breakthrough that's making fusion a reality. Let's put it into context. How does this new kid on the block compare to the nuclear power we already know and use today? Fission. Let's break down the whole process for each one. What goes in, how it works, and what comes out the other end.
When you see them side by side like this, you can see they're basically opposites. For fuel, fission uses heavy, rare stuff like uranium. Fusion, on the other hand, uses light, superabundant stuff like hydrogen. The process? Also opposite. Fission splits big atoms apart, fusion smashes small ones together. Now, both produce a huge amount of energy, absolutely.
But it's that other output, the stuff that comes out besides energy, that is the real game changer.
And that brings us to the elephant in the room. It is probably the most important question, and for sure the biggest public concern when you talk about nuclear energy. What about the radioactive waste? So let's compare the aftermath of these two very different processes.
So let's get this out of the way. Does fusion produce radioactive waste? The simple answer, according to researchers at places like Germany's Max Planck Institute for Plasma Physics, is yes, it does. But, and you have to hear this part, the kind of waste, the amount, and how long it stays dangerous, well, that's a completely different story from fission.
I mean, just look at the contrast here. The waste from fission, that spent fuel, is high-level stuff. It stays dangerously radioactive for thousands of years, and we still haven't solved the problem of where to permanently store it. Fusion waste is totally different. It doesn't come from the fuel at all. It comes from the reactor's own metal walls becoming activated by neutrons. That material is only low to medium-level radioactive, and its hazard fades away in decades, not millennia.
And here's the really cool part. Researchers at the Max Planck Institute are working on a way to create a closed loop. The idea is that after a relatively short cooling-off period, maybe just a year, those activated reactor parts could be recycled and used to build new fusion plants. Think about that for a second. That's a sustainable cycle, not a one-way trip to permanent storage deep underground.
So, let's put it all together. The magnet problem is solved and the waste profile looks way more manageable. And because of that, the world of fusion has totally shifted. It's not just a far-off science experiment anymore. Now it's an all-out engineering race to see who can get the first commercial plant connected to the grid.
And the timelines are getting shorter and shorter. A project called SPARC, which is a collaboration between MIT and Commonwealth Fusion Systems, is aiming for what they call their Kitty Hawk moment, right in the middle of this decade. That's the historic first time a fusion device will produce more energy than it consumes. From there, the vision is to scale up and scale up fast. The big goal? Maybe 10,000 fusion plants online by 2050, providing a fifth of the whole world's energy.
You know, Dennis White from MIT put it perfectly. He said fusion could be the last energy source we'll ever need. And that's the ultimate vision, isn't it? A world powered by the same clean, safe, and nearly limitless energy that powers the stars? An end to our reliance on digging things up from the ground to burn them? The science is advancing faster than ever, and the engineers are racing to catch up. And it leaves us with this one big final thought. For all of human history, our progress has been tied to mastering fire. For millennia, we've advanced by burning things. So the question is, are we as a civilization finally ready for the next great leap? Are we ready to bottle a star?